Hello chemists, this is Ms. Blachino and you are watching Screencast 6.7 on empirical and molecular formulas. In today's lesson we're going to look at how to use percent composition by mass data in order to figure out the empirical and molecular formulas of a compound. This is actually pretty cool that we can take percent composition by mass information and essentially work in reverse and figure out what the formula of an unknown compound could be. The way we get this data is through something called combustion analysis, and for those of you who like to light stuff on fire, this would be right up your alley. Basically, this is a technique that involves igniting a sample and then you collect the products. So if you take a sample that is flammable and you burn it, you're going to get the oxygen to react with different aspects of that molecule or the different elements that are present. For example, if you burn something like methane, CH4, you make carbon dioxide. That's because the carbon reacts with oxygen, and you could also make water. That's because the hydrogen reacts with the oxygen. And after you burn it and you push the gases through, you've got a couple different I guess you can kind of think of them as like Brita filters almost, and they're going to collect certain specific products of that combustion reaction. And then based on the mass of the sample you started with and the mass of the different molecules or products that are absorbed, you can work backwards and figure out what the empirical formula and possibly the molecular formula of that unknown sample might be. So unfortunately, we don't have the equipment in class to actually go ahead and do combustion analysis. I know we light plenty of things on fire, but this is different. You've got to be able to collect your products to do something meaningful with it. Instead, we're just going to look at the data from combustion analyses. Empirical formulas. Let's get some terminology out of the way first. An empirical formula provides the ratio of atoms of each element in a compound in lowest terms. It's really the key here, lowest or simplest terms. We can find the moles of each element present within the compound based on our percent composition by mass data or our combustion analysis data, and we can work backwards to get the empirical formula. For example, the formula C6H12O6, which you might recognize as glucose from biology, is not an empirical formula. If you take a look at that formula, you can very easily reduce this down into lower terms. So I've got a 6 to 12 to 6 ratio. I can simplify that to a 1 to 2 to 1 ratio, giving me CH2O. Now when I take that empirical formula and I multiply all the subscripts by 6, I get my molecular formula, but this is a empirical formula because we can't reduce those subscripts down any further. Molecular formulas are a little different from an empirical formula. A molecular formula is going to provide you with the actual number of atoms of each element in a compound. So this will not necessarily be in lowest terms. If you take a look at the formula for caffeine, C8H10N4O2, we can see that this is possible to reduce it down. I could take all of these subscripts and divide it by 2. So what I've got for caffeine here is its molecular formula. And if I wanted to come up with an empirical formula, I can just divide by 2, and I'd get C4H5N2O. So our molecular formulas really just, in most cases, you can take your subscripts and multiply them by a whole number, and that will get you to the molecular formula. Oops. In order to take the empirical formula and determine the molecular formula, you need to know the molar mass of the compound. Without that piece of information, there's really not too much you can do. All right, let's go ahead and try some practice problems where we're trying to figure out empirical and molecular formulas. All right, in your workbook, I think I'm going to start on this question. I'm going to look at question number 4 about nicotine. We're told that nicotine has a molar mass of 162.3 grams per mole, and we've got its breakdown as far as percent by mass is concerned. We're going to try to find both the empirical and molecular formula. You really can't jump to the molecular formula without first finding the empirical formula. So we're told that we've got carbon, hydrogen, and nitrogen present. So that means I'm going to have to use those 3 pieces of information in order to figure out the empirical formula. So what I like to do is set it up carbon, hydrogen, nitrogen. That way I know what I'm going to be working with. You always want to assume that you have 100 grams of your sample. Percentages aren't too useful for us in this case, but if we assume we're working with 100 grams of nicotine, and we're told that 73.9% of it is carbon by mass, I would know that that means that 73.9 grams of that sample is made up of carbon. It's going to be difficult to compare grams to grams as far as the elements go. We know that carbon, hydrogen, and nitrogen have different molar masses, so we can't do it just based on weight. Just like with almost everything we've done this unit, your first step is to try to get to the mole. So we're going to use the molar mass of carbon. In most cases, you can just round to the nearest whole number. So you can figure out if you have 73.9 grams of carbon, how many moles of carbon you would have. And I do not care about significant figures here at all. Take a bunch of them, as you will most likely need them. Not bad. I get about 6.16. I'll do the same thing for hydrogen. I know that it's 8.7 grams by mass. I know that if I have 1 mole of hydrogen atoms, they have a mass of about 1 grams. Pretty easy math here, 8.7. And finally, with nitrogen, if it's 17.4% by mass, and I assume 100 grams, I have 17.4 grams. Sorry. And I know that 1 mole is equal to 14 grams. I can go ahead and punch that in my calculator, and I come up with 1.24. Now, technically, all of these should be in moles, as grams will cancel out and leave you with an answer in moles. What we need to do in order to find the empirical formula is get a 1 to something ratio. So in order to do that, we're going to take the moles that we've calculated, and we're going to divide by the smallest number of moles. So in this case, I've got 6.16, 8.7, and 1.24 moles. 1.24 is definitely the smallest. Moles will cancel out. And hopefully when I perform these divisions, I end up with numbers that are pretty close to whole numbers. When I take 6.16 and divide by 1.24, I get about 5. 8.7 divided by 1.24 is pretty close to 7. And 1.24 divided by itself is, of course, 1. These three numbers become subscripts. So I know the empirical formula for nicotine. And I'm just going to write EF over the top of it for empirical formula is C5H7N. The question is asking me to find the molecular formula. So what I need to do is find the molar mass of the empirical formula. 5 carbons, that's 5 times 12, that gives me 60, plus nitrogen, that makes 74, plus 7 hydrogens, this is about 81 grams per mole. I know that the total molar mass of the actual compound nicotine, not just the empirical formula, is 162.3 grams per mole. So I'm going to take 162 and divide it by 81. It's 162.3 technically. When I do this division, I end up with pretty darn close to 2. You can imagine if I was a little bit more specific or precise with my molar masses of carbon, hydrogen, and nitrogen, I might get this to be exactly 2, but this is plenty close enough for our purposes. This is telling us that we need to take our empirical formula and we need to multiply the subscripts all by 2 in this case to get to the molecular formula. So if I take 2 times 5 is of course 10. I have 14 H's as 7 times 2 is 14. And 2 nitrogens. So I've got my molecular formula, C10H14N2. That's all there is to it. In my opinion, finding the empirical formula is a lot more involved, so let's go ahead and try another practice problem. Let's go up to number 2. A compound consists of 25.9% nitrogen, 74.1% oxygen. What is the empirical formula of this compound? All right, let's try it out. So I know that I'm going to have to solve for nitrogen and for oxygen. I want to assume that I'm working with 100 grams of this compound, so my percentages can turn into masses. I need to convert into moles. Nitrogen and oxygen have different molar masses, so I need to convert into a unit that's going to allow us to compare them directly. And some people like to just kind of go all the way through with one element before they get to another. I'm not particularly picky about what you do. Just make sure that you're showing your work. I get 1.85, and I get 4.63. Of course, these are moles. I need to get a 1 to something ratio. And the way I'm going to do that is by dividing by the smaller of the two numbers in this case. 1.85 divided by itself is 1, and 4.63 divided by 1.85 is, it's about 2.5. It's not close enough where I can really round up or round down, kind of like in no man's land here. I can't have a fractional subscript. You've never seen it before, and it's not like we're saving it for some advanced level of chemistry. You simply cannot have half of an oxygen atom. What you need to do in this case is find a way to keep this ratio of 1 to 2.5 in terms of nitrogen to oxygen consistent, but you need whole numbers. If you're thinking you could multiply this by 2, you are 100% on the right track. That'll give us 2, and 2.5 times 2 is 5. So we end up with an empirical formula of N2O5. There we go. Careful with stuff like that. I can get a little bit tricky. You can imagine if you came up with, let's say, 2.33 instead of 2.5 when you go to do that division, that multiplying by 2 isn't going to be very helpful, but multiplying by 3 should be very helpful. So you just have to get a little creative here and make sure that you end up with whole numbers while keeping that ratio of atoms constant. All right, that really wraps it up for this lesson as far as finding empirical and molecular formulas. Needless to say, you've got some more practice problems on this page, and I recommend that you get them figured out. I'm going to ask you a question like this on your test. Thank you for tuning in, and I hope you found this screencast helpful.